Hello everyone. Today I'm presenting LifeStream, a high-performance stream processing engine for periodic streams. This is a collaborative effort between University of Toronto, Vector Institute, and Sick Kids Hospital at Toronto. In recent years, hospitals are increasingly adopting data-driven technologies like automated patient monitoring systems, personalized treatment based on patients' past health record, as well as statistical and machine learning models that can do risk prediction, like cardiac arrest. Most of these technologies are powered by physiological data collected from patients. Hospitals collect large amount of physiological signals like blood pressure, ECG, and EEG using monitoring devices attached to their patients. These devices periodically take measurements and generate data points at fixed frequencies. For instance, blood pressure is sampled at 125 Hz, and both ECG and EEG are sampled at 500 Hz respectively. Because the data is generated periodically in a streaming manner, we call them periodic streams. Even though there are several other similar datasets, there are certain things that make physiological data processing especially challenging. First of all, hospitals generally prefer to keep their datasets private in order to comply with data privacy protection laws. That means any data processing on physiological signals must be conducted using limited computing power available within hospital facilities. Therefore, the data processing system that we use must make the best use of available computing resources and provide really good performance out of it. Second, physiological data processing pipelines are composed of a wide variety of temporal operations. To give an example, a sliding window-based signal normalization is a commonly used operation to deal with noises in the signal stream. A more complex example would be running peak detection algorithms on top of blood pressure or ECG signals to identify patients' heartbeat. As you can see in these examples, time is an integral part of all these operations. Therefore, the data processing system must provide a programming interface with implicit support for temporal operations in order to make it easier to write these type of computations. Given these challenges and constraints, let's look at few of the currently available frameworks that are suitable for physiological data processing. Since we are dealing with streaming datasets, using a stream processing engine is a natural and obvious first choice. Modern stream processing engines provide rich temporal query language support, using which we can write complex data processing pipelines. For instance, the previous normalization operation can be written using the following query. First, on the input stream, we define a window of size, say, 10, and then compute two aggregate functions, mean and standard deviation. Then join these derived aggregate streams back to the original input stream and update the signal values using a select operation. As you can see in this example, stream processing engines provide these simple yet powerful primitive temporal operations, which can be composed together to build more complex stream processing queries. However, we observe that modern stream processing engines are extremely bad at efficiently utilizing available hardware resources. We analyzed the single machine performance of 4 state-of-the-art stream processing engines and find that they are about 1 or 2 orders of magnitude slower compared to corresponding implementations available in numeric libraries like SciPy. This shows that modern stream processing engines are far from utilizing the full potential of the hardware it is running on. This brings to the second choice of framework, which is to write ad hoc stream processing pipelines using numeric libraries. Libraries like Pandas, NumPy, and SciPy provide a large collection of signal processing operations, which are hand optimized to take advantage of advanced hardware features like SIMD instructions to provide high performance. However, these libraries are not originally designed for handling stream processing, neither do they have support for temporal operations. Therefore, writing stream processing pipelines using these libraries involve a lot of bookkeeping at application level in order to maintain the timestamp of all the intermediate events generated in the pipeline. This makes these pipelines extremely hard to maintain as well as highly error prone. So both these choice of frameworks either fail to be a good fit for physiological data processing from a performance aspect or a programmability aspect. This brings us to LifeStream, whose goal is to provide a rich temporal query language support to write complex stream processing pipelines, at the same time efficiently utilize the available hardware resources to provide extremely high performance. LifeStream achieves this superior performance by performing optimizations that takes advantage of the periodic nature of the data stream. Before we go into more details about LifeStream, it begs to answer the question why traditional stream processing engines are so inefficient. To answer this, let's take a sample stream processing pipeline. Say we have a 500 Hz signal stream, and we perform a shift operation on top of it, which shifts the timestamp of the events by a constant factor, 10 in this example. Then we perform a window-based aggregate function, and finally joins the output with another 100 Hz signal stream. Join operation joins the input events with their timestamps as the key. The first issue with stream processing engines is that they fail to properly preserve cross-operator cache locality. To illustrate this, let's only focus on the first two operations in the pipeline. Traditional stream processing engines are designed to process stream events in batches of arbitrary size defined by user. So the shift operation takes the first batch of events and generate corresponding outputs. Then the stream processing engine eagerly schedules the next operation to run. The aggregate operation takes the first window of events and aggregates them and produces the first output event, then proceeds to the next window of events. Since there are two events missing in this window, the aggregate operation won't be able to generate the next output event. In fact, it has to wait until the shift operation processes the next batch of events. This back and forth between operations completely destroys both data and instruction locality of the query. Moreover, the events that are already present in the window need to be stored locally by the aggregate operation until it receives the next batch of input events. This means the operations need to perform runtime memory allocation and deallocation, which adds significant overhead during query execution. Finally, most stream processing engines follow an eager query execution pattern, and this can cause redundant computations in the presence of discontinuities in the input streams. Let's say there is a gap in the 100 Hz signal stream. Since join operation only cares about strictly overlapping events, there is going to be a gap in the same region in the final output stream as well. That means the join operation needs to throw away the events that falls into the same regions from the other side, rendering any prior computations on them completely wasteful. This is especially a problem with physiological data processing, as data scientists often want to join multiple signal streams together after performing a sequence of compute-heavy operations on each of them. This figure shows the data distribution of blood pressure and ECG signals collected over a 6-month period. As you can see in this figure, the strictly overlapping regions of both these signals are far smaller compared to the total data size. This non-uniform data distribution causes significant amount of redundant computation in traditional stream processing engines. We solve these issues in LifeStream with the help of 3 query optimizations. And the basis of these optimizations is what we call the linearity property of periodic streams. Linearity property simply state that temporal operations on a periodic stream follows a predictable linear mapping between the events in the input stream and the output stream, as shown in this figure. One consequence of this property is that the output stream produced is also going to be periodic. Therefore, we can recursively apply this property and extend this mapping throughout the entire pipeline. LifeStream uses this property to propose 3 query optimizations. namely locality tracing, static memory allocation, and targeted query processing. Let's start with the first one. Instead of executing the query on arbitrary sized batch of events, LifeStream uses this method called locality tracing to identify the right granularity for each operation in the pipeline, such that the end-to-end locality is maximized. For any given sequence of events in the final output stream, LifeStream follows the linear mapping to identify the corresponding parent intervals of events. These intervals defines the granularity of each of those operations. Operating on these intervals means that the intermediate events generated are going to be fully consumed by the immediately following operation. This maximizes the end-to-end data and instruction locality of the entire pipeline. Once these intervals are defined, LifeStream tries to estimate the memory required to store these intermediate events generated. Since we are only dealing with periodic streams with fixed frequencies, the maximum number of events that can be present in any of these intervals can be statically computed. LifeStream then pre-allocates the memory required to store this event during query compile time, and then keep reusing them during runtime. This almost entirely eliminates the memory management overhead during query execution. Finally, to deal with redundant computations in the presence of discontinuities in the input stream, LifeStream follows a query execution pattern called targeted query processing. In this method, LifeStream uses the linearity property at runtime to trace the regions of input streams that are expected to produce output in the final output streams, and then selectively execute the query only on those regions. This allows LifeStream to skip over the events in the input streams that are expected to produce redundant computations during query execution. We implement these three optimizations in LifeStream using C# language and .NET framework. For more details about these optimizations and the query language that we support in LifeStream, we encourage you to take a look at our paper. On top of this, we also provide a collection of common physiological data processing operations as part of our library. We also provide primitives that can perform pattern recognitions on top of signal streams, as well as easier ways to integrate LifeStream with third-party libraries and external frameworks. We evaluate LifeStream and compare it with two strong baselines. Trill is a state-of-the-art stream processing engine specifically optimized for single machine performance. We also compare LifeStream against hand-tuned implementations available in numeric libraries like SciPy, NumPy, and scikit-learn. As for benchmarks, we collect a set of micro benchmarks containing commonly used signal processing operations, and we combine these operations to build a full end-to-end stream processing pipeline. We run these benchmarks on physiological datasets collected from Sikit's hospital, and we run them on hardware configurations available both in hospitals as well as in AWS EC2 instances. First, we measure the single thread query execution time on operations benchmark as well as end-to-end application, and find that LifeStream can perform 7.5 times faster compared to Trill and 3.2 times faster compared to numerical libraries. One interesting takeaway here is that on individual operations, LifeStream can achieve at least 50% of the performance of hand-tuned versions available in numerical libraries. In some cases like normalization operation, LifeStream even outperforms the hand-tuned version by about 35%. On the end-to-end application, on the other hand, LifeStream showcases much higher performance gains over numerical libraries. And the key reasons for this being, numerical libraries, similar to traditional stream processing engines, does not support cross-operator optimizations. Moreover, different libraries follow different data representation formats. Therefore, stream processing pipelines written using numerical libraries suffer significantly from data conversion overhead. LifeStream avoids these issues by following a common data representation format across all the operations. We also employ cross-operator optimizations like locality tracing. Next, we measure the scalability of LifeStream by taking advantage of the data parallel nature of the workload. We scale up the computation by increasing the number of parallel threads of execution in a single machine, as well as distributing the workload over multiple machines. And we find that LifeStream is more than 8 times better scalable than Trill, and about 1.73 times better scalable than numerical libraries. We also observe that due to higher memory pressure, Trill cannot be scaled more than 11 threads in a single machine. While both LifeStream and numerical libraries can be scaled up to 32 threads, which is the maximum number of cores available in that machine. Finally, we evaluate the generality of LifeStream by implementing 2 real-world models that are used at Sick Hospital. Line 0 is an artifact detection model that runs on blood pressure signal, on which LifeStream achieves about 11 times faster performance compared to Trill. CAP is a cardiac arrest prediction model, which runs on 6 different signal streams, and LifeStream achieves 5 times better performance compared to Trill. This shows that LifeStream can handle diverse data analytics requirements, at the same time provide superior performance. We have more results in the paper. For instance, we conduct a sensitivity study on individual optimizations in LifeStream and show that locality tracing can reduce last level cache misses by about 3 times, and targeted query processing can further improve the performance by about 35%, depending on the degree of overlapping between input streams. We also have an extensive qualitative comparison against other frameworks like time series databases and stream programming languages. And we show that LifeStream is better suited for physiological data processing, both in terms of programmability and performance. To conclude, physiological data processing using traditional stream processing engines is extremely hardware inefficient. To address this problem, we propose LifeStream, a stream processing engine which employs end-to-end optimizations like locality tracing, static memory allocation, and targeted query processing, which takes advantage of the periodic nature of the physiological data. We evaluate LifeStream using real workloads and real datasets collected from Sick Hospital, and compared to a state-of-the-art stream processing engine Trill, LifeStream achieves 7.5 times faster performance, and compared to hand-tuned implementations available in numerical libraries, LifeStream achieves 3.2 times faster performance. Before I conclude, I would like to announce that LifeStream is currently open source, and the source code is available in the following GitHub link. Thank you for listening to my talk.